Welcome to another exciting educational video brought to you by Upvision Concepts Academy. So today we'll be looking at metals and their compounds. In this lesson, we will see the properties of metals, we'll see how metals are extracted, and we'll dive into the corrosion and prevention. Then we'll look at past questions and answers. So sit tight and enjoy this video. Don't forget to like and subscribe to our channel to get more of our content. Okay, so the first thing we'll see under metals and their compounds are the properties of metals. Properties of metals. Recall when we did periodic table, you saw a section of the table where you have metals, and we see that metals are elements that readily lose electrons. So metals readily lose electrons. Okay, so they lose electrons to form positive ions. So they are typically found on the left part of the periodic table, on the left side. The right you see non-metals. So general properties of metals is number one, properties of metals. So the first one, generally they are good conductors of heat and electricity. They are good conductors of heat and electricity. Okay. Secondly, they have high melting points. High melting points. Melting, I will include and boiling points together. Melting and boiling point. That means their temperatures are extreme. Extreme melting point and extreme boiling point. They are malleable. Malleable. That means malleability here means that they can be hammered to shape. Malleable can be beaten into sheets. Into sheets. That means at high temperature you can reform them to shape. Okay, so they are ductile. Ductility means that they can be drawn to shape. I can elongate metal. I can it can be drawn into wires. Drawn into wires. That's the word. Drawn into wires. So they are ductile. They are lustrous. Lustrous. L-U-S-T-U-T-R-U-S. Lustrous. What does this mean? It has shining appearance. Shining appearance. Okay? So that is for metal. They are sonorous. Okay, I'll look for a place to put it here. Number 6 point. Sonorous. This talks about music. Sonorous. Okay, so that means you can make melody sounds. You produce sounds when struck. Produce sounds when struck. Okay, so number 7, they have high density. Okay, so there's exception for this one, except for alkaline like sodium. So they have high density. High density. High density. So the exception is for alkaline metals like sodium. Sodium does not have. So these are the properties, physical properties of metals. So we move on to chemical properties of metals. And we say, number 1, that they react with acid to produce salt and hydrogen. So they react with acids to produce salt and hydrogen. So I would say a case in example is hydrogen gas, of course. So a case in example is when zinc, which is a metal, reacts with acids, hydrochloric acid, it forms zinc chloride and hydrogen is liberated. So this hydrogen gas liberated. So yes, so this is the acid, and this is the salt. So zinc reacts with acids to give us salt, and hydrogen is liberated. Okay, so on that chemical reaction that metals normally go through is that it reacts with oxygen to form oxide. It reacts with oxygen to form oxides. Okay, so an example of this is when magnesium and oxygen reacts, and we're getting magnesium oxide. Okay, so then another thing is that in the group of in the periodic table, there's a pattern of reactivity of metals. Reactivity decreases down the group and decreases across the periods. Reactivity increases down the group and decreases across the periods. Decreases across the period. So what's responsible for this kind of behavior? You know, because down the group, you have more shares are added. More shares are added. So down the group, you are having an electron at the outermost share, which is farther from the nucleus. So the electron can easily be liberated because the atomic radius is big. Okay, so if I have two elements for metals, for instance, this is the nucleus. This one has one electron at the outermost shell, and another one, nucleus, first shell, second shell. This one has one. So both of them have one at the outermost shell. They are in the same group, but this one will react faster because the distance between the central nucleus and the electron is greater than this one. So that distance, you see that the attraction to cause stability, the attraction between the central nucleus and the electron is higher for this one because the distance is small, but lower for this one because this one is distance is high. So this one will react more because the electron can easily come out, can easily be donated, because we say that metals actually becomes ion when it loses electron. It easily loses electron. Understand? So the ease of losing electron increases down the group. That ease of loss of electron is what is responsible for its reactivity. Understand? But across the period, because across the period you have more electrons in the atmosphere, you will see that there is tendency for affinity to the central nucleus. So the reaction becomes difficult even as it goes across the period. Okay, so we'll go into the next one. How do we extract these metals? How do we extract metals? Okay, so metals occur in natural ore that's either as free elements, that is native state, or in compound, that is a combined state. Okay, so we're interested in that combined state. How do we take it out of the combined state? The method of extraction depends on the metal's position in the reactivity series. Okay, so for iron, we'll just take some of the metals in question. Number one, iron. Let me write iron. Iron, the chemical formula is this. That's how we write it. So it can be extracted from this compound, iron oxide. You can call this hematite in a blast furnace. In a blast furnace. So we'll look at this more in industrial chemistry, and we'll see all these processes where elements are created. So for the industrial process, for the extraction of iron ore from the ore, the steps include, sometimes you'll be asked in your theory to write out the steps. The first one is that the ore now is this one, the mixture of iron and this the compound, the elements, is mixed with coke and limestone. with coke. Coke is not the Coca-Cola. Coke and limestone. Okay. So when you mix this limestone with ore, the next thing is that the coke bonds. The coke bonds to give carbon dioxide. The coke bonds to give carbon dioxide. Okay. Okay. So carbon dioxide is now reduced to carbon monoxide. Okay, I'll just say carbon dioxide is reduced to carbon monoxide. Third step. So carbon monoxide reduces the iron oxide to form iron and carbon dioxide again. Okay, so this one, carbon monoxide, reduces iron oxide to iron. Okay, so this is the presentation. You have this formula like this, plus carbon monoxide. I will now have iron coming out, 2 of it, and carbon dioxide, 3 of it. Okay, so at this point, at this stage, you will now introduce limestone. We talk about limestone here. Limestone is actually this. This is limestone. Calcium carbonate. Calcium trioxocarbonate 4. So you introduce limestone, and when you introduce limestone, limestone actually decomposes to calcium oxide, and calcium oxide is reacted with silicon oxide, and slag is reproduced. Okay, so but our intention, this is what we are looking at. We are looking at this one. This one has come out already. But the byproduct, you have the byproduct as slag. This is slag, calcium silicates. Okay, slag. So that's how it is produced. Okay, so iron is extracted from iron ore in a blast furnace. That's what we should know. The next element, metal we are going to look at is aluminium. So iron and aluminium are both what is mostly covered in this syllabus. So we'll look at how aluminium is extracted. So the next one is aluminium. How do we get aluminium? From bauxite. So aluminium is extracted. It's extracted from bauxite. So bauxite is actually an oxide of aluminium. This is bauxite. Okay. So the first thing is you use, okay, how? By electrolysis. We'll look at electrolysis soon. So that's the method. So the steps for extraction of aluminium from bauxite through electrolysis. Number 1, bauxite is dissolved in molten cryolite to lower melting points. Bauxite is dissolved in molten cryolite to lower melting point. Then number 2, second step, this molten cryolite, you undergo electrolysis. Electrolysis of the molten. I was looking at the spelling of electrolysis of the molten mixture yields. So for electrolysis, please, there's a video on electrolysis. Just when you are subscribed to our channel, you will see the video. The video will be out in a short while. But electrolysis will be explained in full. But you know, there are two nodes for electrolysis. You have the cathodes. Cathode is where you have the negative pole, the cathode, and the anode is where you have the positive pole. I'm going to write out the products that are going to be liberated on these two poles. So for electrolysis of molten mixture of this bauxite. At the cathode, you will have the aluminium metal deposited. This is the reaction there. And at the anode, you have oxygen liberated. Okay? Oxygen plus 4E. Electrode. So this is the electron. So this is how it splits. So this is where we collect the aluminium at the cathode. So aluminium is deposited at the cathode, and oxygen gas is liberated at the anode, which is consumed and must be replaced regularly. So this is how aluminium is extracted from bauxite. So we move on to reactivity series. Reactivity series is actually the list of metals arranged in decreasing order of reactivity. So there's a chart, there's a series from top to bottom. The top has the most reactive metal, and the bottom has the least reactive metal. So in chemistry, you need to know the order in which metals are placed in reactive series. You will see that in reactivity series, you see that the one at the top is the one that reacts, most. And most times we use this chart to displacement reaction. The one at the top can displace the one, under. Okay. So I'm going to write out this reactivity series. Please do well to have a way of memorizing it. You can use a mnemonic, for instance, a song, anything. But I have a way of writing this out without even looking at any reference material. So the reactivity series goes in this order: potassium, sodium, calcium, magnesium, aluminium, zinc, iron, lead, hydrogen, copper, mercury, silver, and gold. All right, so potassium, sodium, calcium, magnesium, aluminium, zinc, iron, tin, lead, zinc, iron, lead, hydrogen, copper, mercury, silver, and gold. So this is actually series going down this way. This potassium is the most active, most reactive metal, and gold is the least reactive metals. So what's the implication of this? It shows that metals higher in the series can displace those lower in the series. For example, if I have zinc and reacting with copper sulfate, understand? You see that my product will be zinc sulfate plus copper liberated. Understand? So in this reaction, zinc will easily displace copper. Why? Because zinc is higher than copper in the activity series. So this reaction will occur because zinc will displace it. Displacement means that it will take this place of copper, and copper will get out and go and stay on its own. That's displacement. So this is very, very important. They can give you different kind of reactions and say which one is displacement reaction. It's activity series that we are going to use. Activity series. Know the order, the ranking. Potassium is most reactive, followed by sodium, followed by calcium, followed by magnesium, followed by, in that order. This is reaction. How very reactive all these metals are. So again, another implication, apart from displacement reaction, let me just put implication. Displacement reaction. I've talked about displacement reaction. So we can know how which element can displace which one. Understand? Another application of this reactivity series is that metals above hydrogen. Where is this hydrogen? Metals above hydrogen reacts with dilute acid to release hydrogen gas. So all these guys up. So I would say metals above hydrogen, okay, reacts with dilute we dilute acid, okay, to release hydrogen. Again, from this rule, you see that any metal above hydrogen, that means you have to know this, any metal above hydrogen will react with dilute acid to release hydrogen. Then metals below hydrogen, what happens to them? They do not displace hydrogen from acid. Okay, so I'll put it on the board. I'll say metals below hydrogen do not displace hydrogen from acids. Okay, so note these three rules are applied to reactivity series. So we finally wrap up this lesson with this subtopic, corrosion and prevention. So what is corrosion? Corrosion is the gradual deterioration of metals due to reaction with moisture, oxygen, or other chemicals. You know, we said that metals are actually lustrous, that is shining. You know, in raw form, pure form is shining. Understand? So, but if after some time it's exposed to moisture, water droplets, oxygen, and other chemicals, you see that shiny, beautiful nature now becomes to be rusty and ugly. Understand? And iron is an example of a metal that is susceptible to rusting. So rusting of iron, I'm just going to write a chemical equation to illustrate that. So if iron reacts with, or is exposed to oxygen, this is oxygen, exposed to oxygen. So what I'm going to be getting, in presence of water, yes, in presence of water, please, let's write this thing very well. So I'll be seeing this iron hydroxide. Okay, let me see. Okay, iron hydroxide. I will see okay, so it will still go further and become this compound. This water attached to this compound with a dot here, we call it water of crystallization. So, but this particular compound is rust. So this iron that is pure has degenerated to something like this. See the process. In presence of, it reacts with oxygen in presence of water. Okay, so these two are the agents that cause rusting. If you are exposed to oxygen and water for a long time, iron goes through this intermediate process, intermediate form, and come rust. This is formula for rust. Iron oxide with water on top of it. So what are the conditions for us to have beautiful metals, lustrous, shiny metals? How do they now become rust? This formula. How do they become rust? So conditions necessary for rust. So I will name them. Rusting. Number one condition is the presence of oxygen. Look at it here. The presence of oxygen. You can say air. So once that one is there, rusting will happen. Secondly, the presence of water, moisture. The presence of water, moisture. Then how do we prevent rusting? How do we prevent rusting? Okay, quickly, you can paint. Number one, you can paint the metal. You can paint it, or you can grease or put oil in on it. Any kind of coating to block the metal from exposure to moist and oxygen or air. On that way, apart from painting and greasing, you can do galvanization. That's the spelling on the board. Galvanizing. Or let me use the word galvanization. Okay, so you can use that one. That is coating with zinc. When you coat the metal with zinc, so you have prevented it from rusting. Then electroplating is another way. Electroplating. So this again is electrolysis, application of electrolysis. So you are coating it with a less reactive metal. That's the you know, we talked about reactivity series. So if you are doing iron, anything that's below iron on that reactivity series, you can use it to coat that iron. Then what they call sacrificial protection, that is attaching a reactive metal like magnesium. So that magnesium is sacrificial. That's the one that will undergo rusting, but the main metal is still intact. All right, so under the description of this video, you will see some past WAEC NECO-JAMB questions with the answers. You can go through them. All the questions and answers are related to this topic. And do well to comment in our comment section. Subscribe if you're not subscribed, so I can get more of our videos. I hope this video has been informative for you. I'd like to thank you.